Welcome to our first video on nuclear physics, that's radioactivity. If you look at this place very well, you see that I wrote physics/chemistry. Why? Because this topic is in physics as well as what now? Chemistry. Now, in this aspect of radioactivity, we want to focus our attention on calculations that comes out in radioactivity. In this video, we are not going to look into the theoretical aspect of radioactivity. There will be a second video where we'll talk about the theoretical aspect. But for now, let's focus on calculations that comes out in nuclear physics or radioactivity. Now, I'm going to divide the calculation in radioactivity into three parts. One part will be called, so I will say part 1. Part 1. Part 1, I will call it mass or quantity or number. Mass, quantity or number, meaning that in this first part of calculation we focus our attention on mass, quantity or number. Now, it then means in effect that when you are asked to calculate mass, it also means you are asked to calculate quantity, or you are asked to calculate what now? Number. Alright? So formula 1, lambda is equal to 0.693 divided by T half. What is lambda? Lambda is what? Decay constant, or you call it the constant rate of decay. And now I can make something the subject of formula here, right? I can make T half the subject of formula. T half from formula 1, T half becomes 0.693 divided by what now? Lambda. So this becomes the formula for half-life. Why this is formula for what now? Decay constant. So this is formula 1. Why this is formula 2. Now, what is this T half? T half stands for what now? Half-life. Of what now? Of a radioactive element. The half-life of a radioactive element is what we call T half. What is the half-life of a radioactive element? Look at this marker now. Let me say that this marker is a radioactive element and is about to decay. Now, at the starting point of the decay, maybe I have original mass of this marker, 500 gram or 500 milligram, depending on the unit. The time it will take for this radioactive material to decay to half its original quantity is what we call half-life. What does it mean? Half-life of a radioactive element is the time it takes for a radioactive element to decay to half its original quantity or mass or value. Alright? Meaning that if this marker was 500 gram, the time it will take this marker to decay from 500 to 250 gram is what we call the half-life. Remember, if it decay to something like 20 gram, it's not yet the half-life. Until it get to half its original value, that is when we call this half-life. And what is the formula for calculating half-life? We say it will be what now? T half becomes 0.693 divided by what now? Lambda. And where lambda is what? Decay constant. Formula 3. Permit me to put formula 3 here. Formula 3 will be here now. Formula 3 is n is equals to 1 all over 2 raised to the power n. Alright, let me write that well. Raised to the power n multiplied by what now, class? N naught. What is n and n naught respectively? The n stands for what? Number. Remember from part 1 I said it can be called mass, quantity or number. Now here that I'm using number, can I also call it quantity? Yes. Can I also call it mass? Yes. So I can say number that remained, that what? Remained after decay, after decay. Number that remain after decay. Meaning that whatever that is remaining after this marker have decayed, that will be what we place here as our n when we are solving calculations. What about this n naught? This n naught here will stand for what now? Original. Original what? Original number. Can I also call it original mass? Yes. Can I also call it original quantity? Yes. Meaning that this can be called mass, quantity, or number, or some texts even call it the count rate. They call it the count rate. Now, having said so, what about this small letter n that we are seeing there? What does it stand for? The n is equal to t all over what? T half. It has a formula. T divided by t half. Of course, I've already said what t is. I've already told us here that t half is what? Half-life, which I have explained. What about this other t? In the radioactivity calculation, we are usually given first time and second time, or we are asked to calculate another time, but we are mostly given half-life. And what is the half-life? T half. When we are given half-life T half, any other time in the question that we are asked to calculate is what? T. That is how we solve question. We can be given this T, we might not still be given this T. So we calculate the T, meaning that when we are to find T, we can find N, then from there we get our T, when the half-life is known. Another important point I want to state here is this. Sometimes the examiner will tell you what number remained after 5 half-lives, or what number is remaining after 3 half-lives. Meaning that in this type of question, your n becomes what now? 5, or your n becomes what now? 3. So I can say that n is what now? Number of half-lives. So if they give you after 4 half-lives, it means that your n is 4. If they say after 5 half-lives, it means that your n is 5. As simple as that. Please, you can pause the video to copy out all these formulas because they are very, very, very important. High yield in the exam. Very, very important. For you to get your accurate answer. Accurate answer. You use these formulas now. Up next is formula 4, which most of you are not familiar with. I'm going to put it up here now. So this is formula 1, 2, 3. Okay, I can title this formula 4 so that next one becomes formula 5. Remember that we are still on what now? Part 1, which is what now? Mass, quantity, or number. Do well to pause the video and copy out all this because I'm going to remove them now so I can continue. Alright? Under this same part 1, look at formula 5. Under part 1, look at formula 5. Formula 5 is this very, very important formula. Look at it here now. 2.3 log n over n naught equals to minus lambda t. Everything in this formula, all the parameters in this formula has been explained. 2.3 log n over n naught. The n here stands for the number that remains, this same n. Why this n is the original number, original quantity. Lambda is the what? The decay constant. Why this t is this same t that you are seeing here. It then means in effect that when I'm given a question and I'm asked to find this time, I will call this time any other time in the question. That is how I describe it. Any other time in the question apart from half-life is this t. So when this t is not known, it means I can go this way by calculating my n, then coming back to substitute the value of n here to get my small letter t. Again, I can as well calculate this t from this formula here, from formula 5. What does this mean? It then means in effect that whatever formula 3 can solve, formula 5 can as well solve. Whatever formula 5 can solve, formula 3 can as well solve. But when do we use any of them? Pay attention to this to make it easier. Use formula 3 whenever you are looking for this n or this n. If you are looking for original quantity, original number, original mass, go for formula 3. If you are looking for the number that remained after the decay, go for formula 3. But when you are looking for time, this small t here, kindly go for formula 5 because it becomes easier to get your t faster and reliable than using that 3. Very soon now, we'll start solving questions on radioactivity. Look at the list of questions we have here. So do well to pause the video and copy out the formulas. Look at these questions here. Alright, by the time we solve this question, you see how these formulas, I'm going to put them into use now. Without wasting our time now, we'll look into other formulas that we find very useful when it comes to radioactivity. But it is important for me to state that first part ends here. If all these formulas, you have them at your fingertip, it means that the first part you can do very well in first part. So I will quickly, without wasting time, take part 2. But before I take part 2, there is another formula I can get from formula 3. Let me do that very quickly here. I said in formula 3 that n is equals to what now? 1 over 2 raised to the power what now? N multiplied by what? N naught. Right? This n now, I can remember in mathematics, if I want to get what is here, or I want to get everything here, look at it, everything here. I can divide this side by this side so that I can get everything here. By so doing now, n over n naught, alright, I divided this side by this side, will be equals to what now? 1 all over 2 raised to power n. Of course, mathematically, whatsoever that should be here, let's assume I don't know the value of our n now. But whatsoever n will be, even if n will be 1 million, 1 raised to the power 1 million will be 1. 1 raised to the power anything is 1. So therefore I can write n over n naught will be equals to 1 raised to the power n is what? 1 over 2 raised to the power what now? N. So that I can do what now? Cross multiply. If I cross multiply 2 raised to the power n multiply this, I will get 2 raised to the power n multiplied by n will be equals to 1 times n naught. So that to get my 2 raised to the power n, 2 raised to the power n will be equals to what class? N naught over what now? N. So I'll write n naught by n. Please take note of this formula. Very, very important. I can call it formula 6 for the first part. But take note that whatsoever formula 6 can solve, formula 3 can solve. And whatsoever formula 3 can solve, formula 5 can solve, and vice versa. You can make use of formula 6 for questions that formula 3 can solve. It is faster and reliable than formula 3. So these are the formulas we need in the first part of this topic. Moving on now. Let's quickly talk about the part 2. I want to write out all the formulas before I start solving questions. Please do well to pause the video and copy out this formula. Otherwise, I'm going to rub it off from there. Moving on. Part 2 of nuclear physics or radioactivity calculations, part 2. Part 2 is what I title as what now? Activity. Now, what is activity? It is important to state that activity is the rate of radioactivity. Activity is the rate of radioactivity. I will spare us a lot of explanation in this because I said I'm focusing on calculation in this first video, so that in the next video we'll talk about the theoretical aspect. Now, what is activity? It is important to state that if you understand part 1, part 2 becomes very easy for you. Why? Because activity behaves like number. Activity behaves like what? Number. Meaning that the formulas I wrote earlier for number, I can rewrite them for what? activity. If I do so now, I will write the first formula now. A will be equals to 1 all over 2 raised to the power n multiplied by A naught. Simple. I don't want to bother us with a lot of notes. What is this A? Just like what we did in number or quantity. This A stands for what? Normal activity. Normal activity. Alright? Normal activity. Why this A naught stand for what now? Original activity. Original activity. Or initial activity. That's A naught. Normal activity A. What of this N? It remains what it is in part 1. You know now the N is still what now? T over what now? T half. So this is formula 1 for activity. What about formula 2? I can write formula 2 as 2.3 log A over A naught will be equals to minus lambda what now? T. Very, very important. It means that activity behaves like number. Just like we saw in number, I just remove the N there and place A. I remove the N naught and place A naught. So it means that activity behaves like number when we solve calculations in radioactivity. Up next now, I'm going to put formula 3 here. Permit me to put it here. Formula 3, very, very important. Formula 3, very important. There is a formula that relates number with activity. Alright, there is a formula that relates activity with number or number with activity, and I'm going to write it here. A is equals to what? Lambda n. Class, what is lambda? The decay constant. What is n? The normal number or the number that remained after the decay. What is A? Normal activity. Meaning that if I rewrite this, if I'm to put N naught here, what will A be? A naught, of course. So A naught will be equal to what now? Lambda N naught. Lambda, decay constant. N naught, original number. A naught, original activity or initial activity. Now look at formula 5, very, very important. Under activity, N naught is equals to N multiplied by NA. Very important. We already said that N naught is the original number, but please take note that in formula 5, I will mark it this way. In formula 5, this N is no longer this N that we described here, which has formula of T over T half. Remember in this case now, this N is what now? Number of half-lives. Why in this place it is not number of half-lives, but rather this N that we are seeing here, this N here, is equal to what now? Number of what? Moles. And when we describe number of moles in chemistry and in physics, we say that the number of moles is equal to what now? Mass over molar mass. The reacting mass of a substance divided by the molar mass will give us number of moles. It then means in effect that I can remove this number of mole here and fix mass over molar mass here. If I do so, formula 5, I will get N naught. Look at it. What am I having here? Number of mole. Can I put this? Yes. Mass over molar mass. I substituted this with this. Because number of mole is mass over molar mass. So multiply by what class? Na. Now the Na, I have not said what Na is all about. This Na there stands for what? Avogadro's constant. Avogadro's constant. And what is the value of Avogadro's constant? It is Na is equal to what now? 6.023 times 10 to the power what now? 23 atoms. If you look at the question we're having here very, very well, look at a particular question is giving us N. This N they're giving us here stands for what now? Avogadro's constant. But please, it does not end here. I'm going to continue driving one particular formula here. Just watch and see what I'm going to get as my final formula. So permit me to remove this part. Permit me to remove here and continue driving. Now look at what I have here. Look at what I have here. I have that N naught is what? Mass over molar mass multiplied by Na. If I solve the mathematics, M times Na will be, so I'll write N naught will be equal to what now? Mna over what now? M naught. Imagine this side is over 1. So M naught times 1, M naught, M times NE, MNA. So that I am seeing that N naught from here, I can make it the subject of formula from formula 4. For formula 4, so let me write from formula 4 below, from formula 4 below, A naught is equal to what now? Lambda N naught. Can I make N naught the subject of formula? Yes. If I do so, N naught will be equal to what now? A naught over lambda. Meaning that I can substitute A naught over lambda into this place. Remove N naught, put the value. What's the value? A naught over lambda. Put it here. So I will have from here now. Look at it from here now. I will have, instead of writing this, I will write this now. A naught over lambda will be equals to MNA over what? M naught. Finally, what am I looking for? Mass. Cross multiply to get mass. If you solve the mathematics, you will get M will be equals to A naught multiplied by what? M naught over, or divide by what? Look at that, look at that. A naught times M naught divide by what now? Divide by lambda times NA. Take note that this formula is one of the most important formula for part 2 when we are solving for activity. So I will number this formula as formula what now? Okay, this is 5. Meaning that will be what now? 6. Please take note of this formula. Very, very important. It is a formula that relates original activity, or you say activity, original activity, molar mass, or sometimes some people take it as what? Mass number. Then again, lambda, which is what now? Then multiplied by Avogadro's constant. Alright. Moving on. Let's look. Please, at this point, part 1 and part 2 is completed. Just pause the video, write out all the formula, because soon we start solving questions with these formulas. Very, very, very important. Now, part 2, if you understand all these formulas for part 2 is settled. Let's move on to part 3 quickly. I might not solve questions pertaining to part 3 in this first video, but in the next video, I'm going to solve questions pertaining to part 3. But for now, let me give you formula for part 3 so that it will be a full package for this topic. Alright. Now, let's move to the big one now. Let's move to the big one. What's the big one? The big one is called binding energy. Binding energy. Binding energy. Without wasting our time, what is binding energy? Binding energy is the energy required to do what now? To separate the nucleus. To separate what? Nucleus. Nucleus. If you, from basis of chemistry and physics, we know that nucleons are also called mass number. Mass number. Mass number. And what is mass number? Proton plus neutron. Proton plus neutron. That will give us mass number. Alright? Now, what is BE, binding energy? Binding energy, BE, it has 2 units. Depending on the unit that the examiner is asking you to calculate it, first of all, binding energy is measured in MeV or in what? Joules. Is it that we calculate binding energy in MeV or we calculate binding energy in what now? Joules. Now, when do we, examiner will tell us the units they want the binding energy to be. Like I said, it is the energy that is required to separate these 2 things, proton and neutron, as simple as that. So what is the formula for binding energy? I'm going to put the shortcut here. By means of shortcut, binding energy is equal to what now? R minus P, close bracket, U. What is this U? This U, 1 U, gives us what now? UAMU. What does it stand? What does UAMU stand for? unified atomic mass unit. Unified atomic mass unit. What about the R and the P there? Our R stands for what now? R stands for what now? Reactants in AMU, in atomic mass unit. What about our P? Our P stands for what now? Products in what? AMU. As simple as that. Reactants in AMU and products in AMU. When do we use this formula? We use this formula when we want to get binding energy in MeV. In MeV. When we are asked to find binding energy in MeV, we use R minus P close bracket U. And what is the full meaning of MeV? MeV stands for what? Mega electron volts. I take that again. Mega electron volts. That's the full meaning. Mega electron volts. It is important to state that 1 U has a value. And what is that 1 U? 1 U, which I'll call U, it is equal to what? 931.5 MeV. What does this mean? It means that in my shortcut, you can write BE equals to R minus P, close bracket, put the value of U, 931.5 MeV. It is worthy of note that you have not gotten energy by just subtracting R from P. If you subtract R from P, what you have gotten is called atomic mass unit, AMU. Because R is in AMU, P is in AMU. And what you have gotten is just change in mass or mass defect, difference in mass. You can only make it energy when you multiply by what value now? 931.5 MeV. That's when you have gotten energy. Then again, this R can never be given in a question. I repeat, this R, which stands for reactants here, can never be given in questions. But this P, which stands for product, is always and must always be given in questions. For questions that doesn't have P, they are mostly incorrect questions. So now take note, P will be given to you, just look at it and take it and put it there, while R cannot be given to you. Since R cannot be given to you, I'm going to put the formula for calculating our R. So that R is calculated as mass of proton multiplied by number of proton plus mass of neutron multiplied by number of neutron. So I'll write the full meaning of all these things now. The MP, or let me just quickly tell you, the MP stands for what? Mass of proton. You don't need to kill yourself. The examiner will give you this. But for the number of proton, of course, number of proton may not be given to you, but depending on the element given to you. Let's assume we are given helium now. Helium is written as 4,2 helium. You ask me now, what is the number of proton here? Is it an atomic number? Yes, so number of proton in helium, in 4,2 helium, is 2. One will be the number of neutron. Number of neutron, of course, number of neutron will be 4 minus 2. That's mass number minus atomic number, which will give me what now? 2 as well. So for helium, number of proton, 2. Number of neutron, 2. But what about the mass of proton and mass of neutron? They are constants and they will be given to you right there in the question. Remember I said we will not take calculation on this until we get to the next video. But for now, we have some questions we are going to solve pertaining to radioactivity. But before I do so, please pause the video to write out all this. I repeat, let me give you the meaning for what this one means. MP stands for what now? Mass of proton. And I said you should not bother yourself. It will be given to you in the question. Why NP, number of proton, which I've shown you how to get. The mass of neutron, you don't need to bother yourself. It will be given to you in the question. Number of neutron, it will also be given. You can get that one from this place by subtracting mass number from atomic number, from basis of chemistry. All right, having said so, This is just for calculating binding energy in what now? In MeV. Kindly pause the video and write out this shortcut because I want to rub off the board now to show us how we can get binding energy in what now? In joules. In getting binding energy in joules, alright, I can wipe this now, yes. In getting binding energy in joules, what do we make use of? We make use of a formula that is called Albert-Einstein's equation. And what is that equation? So I will say getting binding energy in joules now, in joules now, in joules now. We make use of Albert-Einstein's equation. And what is that equation? E is equals to change in mc squared. Of course, this c is a constant, which is what now? Velocity of light, which is what now? C is equals to what now? 3.0 times 10 to the power what now? 8 meter per seconds. That is our C. What about change in m? Change in m is what we call what? Mass defect. Mass defect, or we call it change in mass. Change in mass, delta n, is equal to mass defect, or we call it change in mass. So therefore, it means that change in mass is equal to what now? M2 minus M1. As simple as that. M2 minus M1. So we get our mass defect multiplied by our C squared. We get the binding energy in what? In joules. It is important to state that there is a way of converting our answer in MeV, binding energy in MeV, to what? To joules. That will be in the next video, please. Now, let's do some calculations here now. Let's show some examples in nuclear physics. Look at this question. Look at this question. Or I can pause the video and write out these formulas. Otherwise, they leave here now. Because I want to solve questions at this side. Alright, alright. Now, let's look at these questions. Let's look at these questions. Let's look at these questions now. Now, look at question 1. The question 1 says, two radioactive elements, A and B, have half-lives of 100 and 500 years. Remember what I told you. In physics, whenever you want to solve calculations, write out your parameters. Even in chemistry, very, very important. Write out your parameters. What I can see here is that I am giving element A. Element A, and element A, they say that the T half for element A is what? They say the half-life is what? 100 years. And they also said for element B, look at that, element B, they also said that the T half for element B is what? How many years? 500 years. What did the examiner say I should find? Okay, they said 100 and 500 years respectively. Samples A and B initially contain equal number of atoms, meaning that original value of two of them are the same. So I will call the original value for A N naught, and I will also call this one what? N naught, for their original value, because they said here now that they initially, alright, we said that the half-life of B is 500, half-life of A is 100, and they initially contain N naught, the original quantity they contain initially, since it's same. And that's why I said, let me make it N naught. The T is the time here, the 200 years. I said any other time in the equation aside from the half-life is small letter T. Of course, I'm seeing 200 years. So I'm going to write my small letter T as 200 years. Then look at what they say I should find. What is the ratio of number of remaining atoms? Number of remaining atoms is N. And that of A is what I want to calculate now. So the ratio of the two is the number remaining in A to that remaining in B. Meaning that I'm to find the number remaining in A, find the number remaining in B, and take their ratio. So to get the number remaining in A, it becomes 1 all over 2. Then this N, what will it be for A? So the N for A will be equals to T over what now? T half of A. So it will now be Na will be equal to what's T? T of course is 200 years. Divide by, what is the half-life of A? 100 years. So please take note that whenever we will take T divided by T half, whenever we say N equals T over T half, make sure that these two are in the same unit before you divide. So you can see that this is years and years, so they will cancel. 200 by 100, I will get what? 2. So my N for A, for this first guy, is 2. So I will use 2 in this place. So what's my N now? Since I'm calculating for A, that is 2. So I'll put 2. Multiply by what's the N naught? N naught. Because we are not given. So what will it be now? N for A will be equals to 1 raised to the power 2 is 1. Then 2 raised to the power 2. And that will be what now? 4. Multiplied by N naught. If we do this successfully, NA will be N naught over 4, or 1 over 4 N naught. Or let me put it that way, 1 over 4 of N naught. So what is 1 over 4? If you point our calculator, what is 1 divided by 4? 1 divided by 4 will give us 0.25. So I have it as 0.25 N naught. So that's it, 0.25 N naught. And that will be what should be up. Then let's calculate NB. The same procedure. We'll follow the same way. Permit me to wipe that part. So let me just solve it from there. Yes. So we have see this now. We have N for B will be what now? 1 over 2. Number remaining in B. Raised to the power N multiplied by what? N naught. Solving this now, NB will be equal to that number remaining in B, 1 over 2. How do I get the N? The same way. The N is what? T over what? T half. So for B, the N for B will be, what is T? 200. Divide by, what is T half? Half-life of the second guy, which is, remember they are in years, 500 years. Years cancel years, 200 by 500. Alright, so that's how we get the number of our small letter N for B. So we're going to point 200 by 500. 200 by 500, we get 0.4. So I have my N for B becomes 0.4. So solving with this formula now, going back there, look at the formula. So NB will be equals to what now? Half. Raised to the power, what's my N now? 0.4. 0.4 multiplied by N naught. So what will be NB? Number remaining in B will be, you know, half is the same thing as what now? 0.5. So this is 0.5 raised to the power 0.4 multiplied by N naught. So I will do NB will be equals to 0.5 by, or raised to the power 0.4. What do I get? I will get 0.757 N naught. So I've gotten NA and NB. What will be their ratio? As simple as that. So the ratio, let me put it here. Let me just manage this space and put it here. Finally, our answer would now be N over NB. So NA by NB, number remaining in A over number remaining in B. What would it be now? What's number remaining in A? 0.25. 0.25 N naught. Divide by what's number remaining in B? 0.757. 0.757 N naught. So that the N naught cancel N naught. What do I get there? It becomes divided by 0.25. So our answer will become NA by NB will be what now? 1:3. So 1:3 is our ratio, all right? And that is our final answer. Final answer for this first question. Please take note that the second question that says an element whose half-life is 3 years has n atoms. How many atoms would have decayed after 9 years? We'll solve this in our next video on radioactivity together with this second question. But it is important to note that the second question can be solved, or number 3 question can be solved using the final formula in activity. Look at what they said here. We'll calculate the activity of 1 milligram. This is 1 milligram. 1 milligram. 1 milligram radium-226. So we are going to solve this in our next video. Remember that the 226 there is the mass number. Why we have mass? So remember the formula that connects mass, mass number, or molar mass, and Avogadro's constant. Of course, it is this formula. It is this formula. M is equals to A naught multiplied by what now? M naught divided by lambda times NA. This formula will give us answer for question 3. You can go on and try this using this formula. You get your answer. Drop your answer in the comment section so that by next video when we are going to solve it, you confirm if your answer is correct. So you can use this formula to try this. And again, remember that 1 milligram will have to go to what now? Gram. All right. So thank you and see you in our next video.